Hello, I'm Madeline Weller, and this is my Lab 1 constant velocity for Georgia Tech Physics 2211. For my introduction, purpose, and fundamental principles of the lab. Number one, our lab and layout, and our purpose of the lab is to create a video of an object moving with constant velocity. To do this, I rolled a stress ball across my floor next to a yardstick. I observed that with no force acting on the ball, it moved at constant velocity. Using models, I inputted the video into Tracker, which I used to find the position versus time graph and graph the actual velocity of the moving object. And then I coded the data from Tracker into GlowScript to find the predicted velocity. Models in physics, I compare the data using a spreadsheet and Newton's second law. Okay, so this is the video that I updated into Tracker in the initial conditions of my experiment. So I used a stress ball that was approximately 240 grams or 0.24 kilograms, and I rolled it across the floor in front of this yardstick. I used the calibration stick at zero point 0.5 meters using an inches to meters conversion using the yardstick to find my calibration stick, and then I placed the axes at where the ball was started moving across the yardstick, and then I point mass tracked each frame of the ball to show where it moved, and then create this table on the right. My system is the ball, my surroundings are the floor, um, and then I discussed how I could use the coordinate plane calibration stick and track the point mass to determine the velocity. Main physics ideas for this lab, where we have Fnet is equal to 0 to show constant velocity, and we see this using the velocity update formula of the Newton's second law. We see that velocity final is equal to velocity initial plus Fnet over mass times delta t, but since in this example Fnet is equal to 0, this entire expression is equal to 0, so our final velocity is equal to our initial velocity, meaning velocity is constant. To find the initial velocity, I also use the delta position over delta time function of the first two data points of the tracker. And then I use the position update formula similar to the velocity update formula version of Newton's second law, which is final position is equal to initial position plus velocity times delta time. Here's my experiment encoding details from GlowScript. So this is the code that I used to create the computational model of constant velocity. This initial position is the first data point recorded at t equals 0 from Tracker. And then the initial velocity was calculated using the first two data points of position and time in Tracker. And then my delta t was derived from the frame delta t in Tracker. As we see here, my frame delta t is 0.033 seconds. And then my time final that I used right here is 0.533 seconds because this was the last data point recorded in Tracker as the last point in motion over my determined distance. So this is what I got when I ran the GlowScript code. As we see, the velocity is constant with the slope being constant and downwards because the ball is moving in the negative direction. And here we see that this blue ball moved from the yellow starting point left in a straight line. My conclusions, my data versus model results, and error sources. So since velocity is a slope, we see that the experimental data in red has a slight decline compared to the predicted results. And this could be due in error to the friction from the floor on the ball having caused a non-constant velocity, making the ball slow down. So forces would be equal if there was no friction on the ball and the ball was released with constant force and zero acceleration, which would mean that I would have constant velocity. But as friction acts in the opposite direction of the motion of the ball, it would slow down the velocity of the ball moving across the floor. To answer the additional questions, the what if question, if the axes in Tracker were flipped, then the ball would be moving in the positive x direction. This could also move the origin to the left side, where the ball ended, and all position points would be positive x. So this is what we would see here, is if this origin was moved to the end, we would see the ball is always in the positive x area of the graph. And then our final question, what does it mean? There's an initial force on the ball, but assuming slight friction may cancel out any possible acceleration, the only forces acting on the ball are gravity and the normal force of the floor on the ball in the y direction, which cancel out. However, assuming no friction in an ideal world, the ball will move with constant velocity unless acted on by another force, which is Newton's first law.